Well,
Steve, let me go ahead and introduce you real quick before we get started here, because we've got a couple of things here. So we want to welcome everybody to Vaughan's webinar. It's in the mix, mixing up with the Vaughan Rotamix process mixing systems. Hey, if you're new to our Vaughan webinars, we have a Q&A pod right there at the bottom right-hand side. That's where you're going to put in your questions, and we'll answer those. Most of them we'll probably take at the end of the session. If we catch a couple as we're going through some of the specifics, we'll bring those in. But for the most part, the Vaughan team here will answer those questions at the end. And if you are listening to this as a recording and you have questions, just you can email us at info@chopperpumps.com. That's that part. So let's go ahead and welcome in our two presenters. First, their senior engineer for Rotamix, that's Eric Larson. He's been supporting Vaughan supporting Vaughan customers since 2012. He has a bachelor's degree in civil engineering from Washington State University and is a frequent mixing and processing topic presenter. Eric, you're always a busy guy.
Oh, yes. Especially now with everything going on. Although staying home and staying safe at the same time. So.
That's good. That's good. Well, that's the great benefit of having these on-demand and live sessions. And then let's go ahead and let's get things started. Let's welcome in Vaughan's Rotamix manager, Steve Macomber. Steve's been in the water and wastewater industry, protecting the water environment and public health for over 20 years. Steve, you've been a busy guy.
Wow. You know, it seems like it some days. But I'm glad to be here.
Well, it's good to have you here, sir. And now let me hand over the microphone. It's all.
It's a busy industry. Thanks again, Scott. I think you can tell that I'm excited to be here. Almost jumped the gun there, but thank you all for joining us. Before we start, I just wanted to take a moment to talk about the overall purpose of mixing. You know, everyone here has a technical background, and you all know how engineers especially love to jump right into technical details. And as Scott mentioned, you know, before we geek out, it's just critical to point out that Vaughan understands the big picture around each unique mixing application you have. Mixing is a central process in many industries. You know, on a global scale, the capital and operation maintenance costs are just enormous. So we need to clearly define what each mixing application is trying to achieve before we jump into it. So we do start with understanding that the term, you know, effective mixing means different things to different customers. There's a very real cost associated with both over-engineering and under-engineering, maybe around $1 billion or more per year, pretty easily as an estimate. For example, like many in the room, the purpose of a digester, we all understand, is to break down solids, produce a biogas as predictably and inexpensively as possible. So in the end, there's a most efficient way to mix any application, considering all the capital costs, the operational flexibility you need, the long-term reliability you need, you know, the downtime that could impact permitting, etc. So with all that, I'm going to hand things over to our senior product engineer, Eric Larson.
Thank you, Steve. Welcome, everybody. We're going to get going. So I kind of want to talk about, you know, what are the goals for mixing? What is mixing trying to accomplish? And I think, you know, first and foremost, you know, especially in the headworks of a facility or maybe an industrial, you know, just distributing additives and polymers, different chemicals or other things that you want to disperse very quickly. You may be trying to dilute inhibitive substances, you know, whether it's a digester and you're trying to balance pH, or trying to diffuse some sort of contaminant, you know, in industrial and other applications. Increasing biological contact for suspended growth processes, which is, you know, kind of the backbone of a lot of wastewater processes. And then reducing deposition and loss of process volume. And this is kind of universal. For mixing is keeping things in suspension and helping them move through processes so they're not gumming up the works, and you're able to move solids and contaminants and other substances throughout your process. And then lastly, you want to maximize process efficiency. I'm getting comments that we're hearing two people at the same time.
I got it, Eric. Keep going.
You're good. Okay, perfect. So maximize process efficiency. And so, that's really the goal of mixing, is whatever the process is, if it has mixing as part of the design, you're using mixing to maximize that process and make sure that it's consistent and functions as needed. So some traditional mixing technologies. One of the gold standards in the past was draft tubes. Definitely saw a lot of those installations. Gas injection is also another one that you'll see very commonly. And then submersible mixers, which are fairly ubiquitous in a lot of industrial and agricultural applications. And looking at the polling at the beginning, I think these three were fairly common. I think submersible mixers, unsurprising to me, were very much in a lot of people's facilities. And draft tubes getting a lower share than they may have historically, as they have fallen out of necessarily being the most common technology today. These methods have been around and standard for many decades. A lot of the reference texts have very prescriptive design metrics for these types of systems, and they've been around for a long time. But they can have their limitations. Even though they've been around for a long time, there's still applications where they struggle, and where we can have issues. This in particular is a mixer that probably was in an environment that was a bit too corrosive or destructive for its function. And new processes and operational needs are changing mixing system requirements. As we've tried to endeavor to improve processes and add new technology, the design criteria for the process, especially when it comes to mixing, has changed in some instances. The example there is a picture of a THP process system, which is enhancing biological productivity of a sludge in a digester application, and that has an impact on what the mixing design needs to be, and those sorts of things need to be taken into account when you look at your mixing design. But more specifically today, we're talking about Rotamix, and so we'll get right into what is Rotamix. For those that you may not be familiar, Rotamix is a hydraulic mixing system using a fixed nozzle and an external Vaughan Chopper Pump. It works off of a multi-zone mixing strategy, which is zone 1 is discharging towards the center and reducing, settling in the middle of the tank, and then zone 2, which discharges outwards towards the perimeter, driving the rotation of the tank contents. And this is kind of our standard design and concept for cylindrical tanks, but there's many different tank geometries. While cylindrical is most common, rectangular and custom geometries can also be mixed, but they require varying levels of mixing energy and can be a little bit more challenging because of the geometry not necessarily being symmetrical and conducive to something that is stable in its mixing flow. But even distribution using multiple discharge points is kind of the key to mixing any tank geometry, and we'll get into that a little bit more. You can see an image there of a large egg-shaped digester with a Rotamix system being modeled in Computational Fluid Dynamics. So design flexibility is another key aspect of Vaughan Rotamix. Multiple discharge points create an even distribution of solids throughout the tank and process. And then modeling software and prior experience help determine the most effective nozzle layout, driving the design prior to it actually being installed and built, where once it's built, you really don't have much room to change things if you need to make changes. We also have the ability to mix multiple tanks or zones with one pump. This can be especially helpful in systems where you might have multiple contact basins that are baffled and in a train together for maybe phosphorus removal with an anaerobic and anoxic sections, and various other applications like that where you might have multiple stages and need mixing in all of them, or only some. And the Vaughan Chopper Pump provides all mode of flow and for distribution of flow while also continuously breaking down solids. And that's another key feature for Rotamix, is our ability to take the solids that were within the process and continually break them down and homogenize them as we move through the process, increasing contact and decreasing solid size, which can definitely be helpful downstream as well as you look to dewater or dispose. We've got a really large diagram here of kind of this wouldn't necessarily be seen in a normal treatment plant. As you can see, there's a lot of duplicative treatment processes, but we wanted to kind of show, generally where would everything sort of fall out and where would Rotamix really be applicable. So first and foremost, you have CSO stations, tunnels, main lift stations, inflow headworks, anywhere where you have a large basin that's taking a large amount of flow, but potentially, especially during high flow periods, may have a lot of detention. Definitely a great application for Rotamix. We've done lots of mixing in large CSO shafts, large lift stations, and various other headworks and distribution system, collection system tanks. Next is equalization basins. So once you get through the headworks, if you're trying to regulate flow into a treatment process that might be sensitive to flow changes, or if you've just got a collection basin or equalization basin that's holding flow to maintain your ability to keep the plant below its maximum daily flow, we can definitely provide Rotamix to those not necessarily everyday use basins, and do that in a way that really minimizes clean out and improves performance of those and really dependability, because whenever you have an EQ basin, the last thing you want to do is have your EQ basin down or not functioning, because the whole point of it is for it to be your backup. Anoxic zones, so in the activated sludge, whether it's part of a nutrient removal or just a contact basin, we can do anoxic zones and anaerobic zones throughout those processes and provide Rotamix where you're not going to have your diffused air process available to provide mixing like you would in the activated sludge in the aeration phases. Sludge blending is another good application, and one that really I like to keep separate, and this will be covered in the next webinar in a little bit more detail, but sludge blending is really a different application than solid storage of your digestate, and also a kind of a different application than digestion. Because really what you're trying to achieve is as quickly as possible blending and homogenizing various different sludges with different rheologies and different characteristics, so that you're providing equalized feed to the digestion process. Digesters have been a real good application for us throughout the years. Digesters being really kind of the bread and butter of Rotamix over the years. We have a lot of systems installed, and really just a great application. And then solid storage, definitely seeing an increase in solid storage capacity in the U.S. right now, and potentially in Europe and other areas where you're seeing a lot of restrictions on land application and disposal of biosolids. Definitely seeing a large demand for solid storage capacity as those regulatory issues continue to be fought in the legislature and in policymakers' minds. So some proven applications. Anaerobic digesters, always a proven application for us. Egg-shaped digesters, we've done several large egg-shaped digesters. Generally see these outside of North America. We've done, but they're becoming common and a little kind of everywhere now. You're seeing them more and more. It's definitely a great design, but definitely a little more technical as far as construction and cost. Sludge storage blend tanks, acid phase digesters. We've mixed several acid phase digesters, and we're able to provide full stainless assemblies, both inside and out, and both the nozzles inside the tank and also the pump, which can deal with the very low pHs that you'll see in those applications and provide a really reliable system for those applications where you may need that extra corrosion protection, and even if it's not an acid phase digester, anywhere where you're seeing very low pHs. Secondary digesters, equalization tanks, lime stabilization in clean water facilities, and also wastewater where You may have the clean water people sending all their lime sludge to the wastewater plant and saying, you just deal with it, which I've seen quite a few times. Definitely something that we have experience with and can really be a challenging mixing application. Anoxic zone mixing, septage receiving, definitely the Vaughan Chopper Pump is a great thing for septage receiving, especially if you're getting unscreened trucks, but definitely a challenging application that might require some additional discussion and engineering to make sure that it's as reliable as required by the facility that's purchasing the equipment. Skimming systems, not necessarily DAF tanks where you're getting a very foamy, aerated sludge, but once it's consolidated and you've got a skimming basin, definitely something that we can mix and then pump. And then influent channels and CSO basins are also a very good application for us. So the components, we'll go through the components here. We've got a Vaughan dual nozzle Rotamix assembly there. It's a floor-mounted assembly on a base. It comes with 1-inch thick glass line cast assemblies. So all of the pieces are cast with 1-inch thick ductile iron, and then coated with glass lining to a Rockwell 74C hardness. 3M Scotch Coat 134 fusion bonded epoxy exterior coating for corrosion resistance, and then stainless steel and polyurethane options available. And I will say that our non-stainless standard assemblies have a cathodic protection as well. We have a zinc anode that we attach to provide protection for systems where the design pH is close to 7, but every once in a while you might dip close to 6. It's always good to have a little bit of an insurance policy there. These are covered by a 10-year standard full warranty. It's non-prorated. So, 7-8 years down the line when you're taking the tank down for the first time to do an inspection of the tank, whether you're checking for corrosion of concrete, exposed rebar, whatever it might be, you can rest assured that the nozzles are still under warranty, and that if you have any issues that we'll be there to support you. There's no moving parts in the tank, which I think is a really big thing as far as maintenance goes. Anything that moves needs to be maintained, and I think that's a really big positive is you can get all those moving parts out of the tank where they're more easy to maintain. And there's no scheduled maintenance within the tank. The Vaughan Chopper Pump, mixing flows up to 13,000 gallons a minute. We have self-primer, vertical wet well, and submersible configurations to offer design flexibility. Definitely Scandinavia, anywhere where you've got very cold temperatures, you might not necessarily have room for a pump house or have, especially if you're replacing an existing system. So we can offer flexibility with submersible pumps that would actually go into the pit to facilitate those needs. Where you might not be able to have a pump house in an area where you can get a flooded suction, we can use self-primers. Really, we can provide a flexible solution that will fit the needs of your facility, especially if a traditional flooded suction horizontal or pedestal pump really isn't an option for you. We have multiple seal options, including the Vaughan Tandem Seal, which we'll talk about in a little bit, covering those multiple options. And then we have full or partial stainless steel construction. So if you need a full stainless pump down to the base, for whatever application you have, we can provide that. Or if you just have some corrosion issues where you'd like to look at maybe partial stainless on some key components, that's something that we can facilitate an interchange to really fit the needs of the process and also fit your budget. And then the real key of the Vaughan Chopper Pump is the continual chopping action, breaking down solids within the process and homogenizing whatever sludge or other process fluid you're mixing as the process moves. So talking a little bit more detail at the internals of the Vaughan Chopper Pump, we have the cutter bar here. This is a stationary plate with cutter fingers that cuts against the leading edge of the impeller blades. And the impeller has a swept blade with a leading edge that cuts against the cutter bar and is also self-sharpening as wear occurs. As it wears that edge to a sharp point, which continues to allow for efficient chopping. We've got a cutter nut in the eye of the impeller in that low pressure region. This helps to kick any solids that might try to sit in that low pressure region, and also to cut and anything that might try to bind on the impeller in that low pressure eye region. There's some cutter teeth on the cutter nut that cut against the internal radius of that cutter bar, and provides a good way of dealing with any wrapping that might be occurring on that eye and trying to build up there. We have a pull-out back plate that pulls directly out of the casing, so you can take the entire rotating assembly directly out of the pump casing without disconnecting your piping from the pump, which is really great for any maintenance activity that may need to be done. And the back pull-out also allows for adjustability through these external adjusters to adjust the cutting settings, so that you can do fully external adjustment of all of the cutting clearances as part of your regular maintenance without having to completely take the pump out of installation, which is a huge positive. And we'll talk a little bit about the Vaughan flushless mechanical seal and our seal options. Vaughan has created its own mechanical seal specifically for our pumps. Chopper pumps definitely are a heavy-duty application, and we wanted to make sure that we had a heavy-duty seal that fit the needs of our market. And so we've developed the Vaughan flushless mechanical seal. It's a cartridge-type seal and oil-filled. We have silicon carbide and tungsten carbide seal faces that are available depending on the application, and a Vaughan sales engineer will work with you to determine what's best for your application based on prior experience and the needs of your process. And we've eliminated the stuffing box and cavities behind the impeller with this design, which really helps to take any sludge or solids that might get into that cavity that's generally there, and really keep them out, because that's where you're going to get your problems. That you're going to get cooking of that sludge with the heat from the seal faces and contamination and other issues, and really just trying to get that away from the seal as best as possible is really the best solution. So eliminating that cavity has been a really good idea. It's easily maintained. All that's necessary is that the oil be changed whenever it becomes contaminated, generally every couple months, and what we require is, under regular maintenance, is just monthly check to see if the pressure release valve behind the seal is leaking sludge. Once sludge contamination builds up in the seal, it'll build up pressure, and that pressure relief valve will leak, and that'll be kind of your sign that the seal is ready for an oil change. But all you need to do is change out that oil and put it back into service, generally without disassembling the pump. And if the seal does need to be changed, it's a fairly easy process. It's easy to install. It's a cartridge type seal that just pops right in. Old one pops out, and it's a pretty painless process. In addition to the Vaughan flushless seal, we have the Vaughan tandem mechanical seal. This is a much heavier duty seal that can be important for special applications where you're seeing very, very heavy duty need. It's also a cartridge type seal, water flushed. This is not a flushless seal. This is a water flush seal. And silicon carbide and tungsten carbide seal faces. But in this application, we actually can put tungsten carbide in either the front or back seal, and silicon carbide in the other, and kind of get the best of both worlds there, if that's something that will be helpful for your process. And it also can affect price as well and help save cost. And this is for our most challenging applications, and these are high pressure, corrosive fluids that might have gas entrained and are going to be especially difficult on a seal. Anything where you've got very hard grit that potentially are going to be very very corrosive on a seal. These are the types of applications where you might want to consider a Vaughan tandem mechanical seal, and that's why we offer it. Another component that isn't necessarily part of a Rotamix system but can be very important to the function is a variable frequency drive. It provides system flexibility. As you change the frequency for the pump, you can modify the operational characteristics and mixing energy within the tank, and this can be very important for certain applications, but maybe counterproductive for others, and so we'll kind of get into that. You can fine-tuning mixing energy to current process conditions can be important for variable level tanks. or potentially digesters where you've got kind of competing interests of mixing the tank to maintain the biological process and then mixing the tank to reduce grit deposition and solids deposition, and being able to kind of marry the middle of those two needs. We require VFDs for most digester applications because we really feel that it's a really great way to make sure that you have the flexibility to modify the mixing energy as needed, because digesters especially tend to change over time as the feed changes, as the design loads for the facility change. It's just a good thing to have that flexibility, especially for those applications. And digester applications can see up to 50% reduction in energy costs through the application of a variable frequency drive. That's not something that can be seen by all facilities, but we've definitely had applications where that was able to be achieved. And it's not applicable to all processes. And I think a great example of where you wouldn't want to see a variable frequency drive is in sludge storage or sludge blending tanks, where you really have a defined process. You really aren't going to see benefit from reducing the energy, and you're probably, instead of reducing the energy, you probably want to look at maybe an on-off strategy instead. And so that's something that we'd be happy to discuss with any potential applications with anybody and really talk that through. But those are particular applications where maybe a VFD might not be the greatest idea. And we have specialty assemblies as well that come that are available for Rotamix for different applications. One is an externally mounted adjustable stainless steel nozzle. This can be either adjustable or a fixed variant, and these are for a small fog and high strength waste tanks. So these would be 10 to 30 foot diameter pad mounted tanks above the ground, where you really aren't going to see where you really don't have the space for a Rotamix system, or it might be a little bit overkill. And we have externally mount systems that can be mounted to the tank flanges on the exterior of the tank to make that available. And so I think that's a really great application for those. And then we have the foam buster assembly, which for foam suppression. This is an assembly that generally we'll recommend for digesters, but there may be other applications. But this is a great tool for dealing with minor foaming and foaming issues. We all try to deal with foaming, and we've got a presentation topic coming up in the future to talk about foaming as a larger issue. But even the best systems are going to have foaming every once in a while. It's kind of unavoidable. And having foam suppression installed in a digester really helps to eliminate nuisance foaming when it does occur. And we'll talk a little bit more about the foam buster right now. So foam suppression for digesters. The foam buster evenly disperses droplets over the digester surface. You can see an image here of a foam buster in action. We're actually, usually you won't be able to see the foam buster because most anaerobic digesters are going to be covered. But here's a great view of what it looks like in action. You can see the droplets being spread over a large surface area, really helping to condense any foam that may be building up. And it helps to control digester upsets when they occur. We have an optional scum nozzle which resuspends floatables and prevents stratification in digesters. And scum nozzles can really be applied to other tanks as well, even without the foam buster, to kind of re-entrain and mix any scum blankets or surface layers that might be trying to form. And you can use these with Rotamix or to supplement an existing mixing system to minimize foam and scum buildups. We can sell these as a separate system which operates a pump and just a foam buster, or a foam buster scum nozzle combination that can be installed to an existing tank just to supplement the existing system if that's what's needed. And so that's something that we can also discuss with anybody who has an application. Talk a little bit about fog and high strength waste. Generally you're going to see organics received and blended in a blend tank, whether this is from truck unloading or organic waste from grinders or mills or some other process taking a received organic waste and turn it into something that can be fed into a digester and blended. So Rotamix for the blend tanks, this is where you'd potentially see those externally mounted assemblies and a Vaughan pump driving it. But one thing that we can do is we can meter those conditioned solids into a primary digester through a three-way valve. So you can use a Vaughan Chopper Pump to mix a blend or a feed tank, and then you throw the three-way valve using SCADA and an actuator or manually, and then feed that with the same pump into the next process. So that's something that we can provide flexibility for applications where you're looking to supplement your existing solids, biosolids capacity. And here's some examples of some facilities. The one on the left is in California, where it's nice and warm and everything's outdoors. And then the one on the right is in Illinois, where it's a little bit colder and everything's indoors and maybe insulated. And you can see, fairly simple systems, above ground tanks, a couple precast tank penetrations and pipe spools, and then Vaughan Chopper Pump mounted with external piping running to externally mounted nozzles, mixing those tanks. Talk a little bit about mixing energy design. We were talking earlier about making sure that the process is designed to be as efficient as possible. You want to have the right amount of mixing for the process, but not over design it so that you're wasting energy. And so we'll talk a little about where our mixing energy design criteria come from and what is right there. So mixing energy is the energy required to achieve the process mixing design. I think that's pretty self-explanatory. And there's several suggested values that exist in industry, and specifically for anaerobic digestion. You've got WEFMOP 8, which says 0.2 to 1.5 horsepower per 1,000 cubic feet. You've got Metcalf and Eddy, who have another recommendation of 0.025 to 0.04 horsepower per 1,000 gallons. And if you do the conversion, you'll find out that these aren't necessarily inclusive of each other, and that the ranges are incredibly wide. And other processes may have different mixing energy requirements as well, which kind of begs the question of what is the right answer. And I think the answer is that mixing energy depends on a lot of factors. There's a lot of things that go into mixing design, and it's really difficult to apply a rule of thumb to say every single time you have an application, this is how much energy you need, and don't question it. This is just the right answer. I think that's where you can get into trouble. One of the things that I think is really glassed over by a lot of the standards that are out there is grit deposition in particular. Grit management is not contemplated in most mixing energy standards, and generally, if you look at the little footnotes underneath the textbook, you'll see that it specifically calls out that that's not a consideration just because of how difficult it is to account for. Grit can accumulate if not addressed in mixing system design. If you're not able to resuspend that grit, you're not going to get that grit out of the tank. It is just going to keep accumulating, and eventually it'll completely shut down the process. Grit deposition leads to loss of active volume and increased maintenance, especially if you start to flood your heat recirculation lines or other sludge withdrawal lines with grit. You can really start to destroy pumps and process and other systems if you're giving them a really heavy grit load. It can really cause some damage. And grit and designing for grit is really important, especially in areas with really sandy soils. So deserts, coastal areas, anywhere where you're going to see a lot of grit make it into your collection system or into your process, grit's going to always be a big concern. So how do we design for mixing energy then if there's no standard? And I think for us the answer has always been CFD. We've really focused on computational fluid dynamics to model our mixing system design from the beginning. And every one of our systems is informed by CFD, even if not specifically modeled in particular. We generally model almost every system in CFD, but there's definitely applications where it's a design that we've seen something very similar before, and the customer declines to pay for the CFD work. but always our design is being driven by past CFD, if not one specific to the process that we're modeling. It's the most dependable way to model mixing system design performance, and we've done field testing on various systems and validated the CFD analysis results and shown a very close relationship between what the CFD is showing us and what's happening in reality, which has really helped us fine-tune how we're doing the CFD to make sure that we're getting accurate results. Because with any technology, especially analysis software, if your data going in is bad, the data coming out is bad. And so that's something that we really have prided ourselves on. We have the ability to model customer unique geometry and sludge rheology. That includes things that maybe aren't always considered, corbels within a tank, existing piping, if there's support columns, various other things that aren't really represented when you just say, okay, I have a tank this volume and I want to mix this volume. That volume can be very different depending on what's within the tank and what's potentially having impacts on that. One of the biggest things, though, I think is sludge rheology. So rheology is the study of the physics behind non-Newtonian flow, and really it's behind the physics of fluid flow in general. But I think where it really finds its niche is non-Newtonian flow and the modeling of those for process. Most systems are mixing sludge and not water. You very rarely are you mixing a tank with water. It's generally going to be a sludge. And you're going to have non-Newtonian effects with that are going to affect mixing system performance. Viscosities can greatly impact mixing system performance. So if you take a look at the graph here, here's a breakdown of a couple different sludges that we have in our sludge library. And you can see we've got 2.4 and a 4% digested sludge. And then we're comparing that with a 4 to 5% thermal hydrolysis process sludge, which is so you can see the 4 to 5% sludge is actually less viscous than the 2.4% digested sludge according to the viscosity data. But then you look at things like 6 to 7% thickened waste activated sludge, and now all of a sudden you're up way off the scale. And and where you're seeing mixing tanks generally be, the shear rates within the bulk fluid flow are between usually 0 and 2. And you can see on that left side of the graph, you really have a large variability in your viscosity depending on where you're at on that. So little changes to your mixing design can have big impacts on your mixing performance. And I think that's kind of the takeaway I want you to have from this. And so Vaughan has a library of real sludge data so that we can, as accurately as possible, model the process that you're trying to design, even if no data exists for that process. And if it is an existing system, we have the ability to get samples of that sludge and do the analysis to get that data and then plug that into a CFD to help drive design, especially for applications where there may be no mixing or inadequate mixing, and there's a need to address that inefficiency. An example of this, Salmon Creek Wastewater Treatment Plant in Vancouver, Washington. This was an existing mixing system design that was inadequate. One of the issues here was it was originally going to be a blend of primary and TWAS, thickened waste activated sludge, but the issue was that because of the timing of the processes, it got all primary in the morning and all thickened waste activated sludge in the afternoon. So in the evening, the blend tank was almost all thickened waste activated sludge. And if you look back on the graph on the previous slide, you can see that TWAS is quite a bit different than anything. It's a lot more viscous than what you would see for a primary sludge. So this design was inadequate when it was in the afternoons and it was having issues with mixing. So we were able to do CFD analysis on the very viscous TWAS and allowed for us to more accurately model and determine the required mixing system energy for this system and recommend some changes to the mixing system design. And it's one of those things, if you can address that before you build the tank, you can make sure you can give yourself a lot more flexibility in how you address those challenges than if you're trying to troubleshoot it in the future once it's already built. Another example, this is an example of biogas production, which is always important for digester applications. So this is the Fairfield-Suisun Sewer District in California. It was a replacement of Digester 1, which was a gas injection mixing system. They replaced Digester 1 and then and really only had the budget to replace one digester at that time and wanted to take that opportunity to kind of do a comparison to see if they saw any improvement. A side-by-side comparison with digester number 2, which was getting the same feed but was being mixed by a gas injection mixing system, showed a significant increase in gas production. And overall, over time, over the time of the study, they saw an overall increase of 49% in biogas measured in BTU per kilowatt of mixing energy imparted into the tank. And you know, that's something, especially for facilities that are looking at trying to achieve net zero or reduce their energy usage, or have potentially credits, RIN credits for gas production. It can definitely become a good financial opportunity to look at these things and try to maximize the efficiency of these processes. Talk a little bit about validation in the next couple slides. You know, we recommend, you know, do the CFD on the front end to make sure that you're designing the system appropriately, and then on the back end you need to verify to make sure that the design is operating as required. And so, you know, temperature profile and total solids testing are kind of our recommendation for the best of both worlds in terms of having that validation, and doing that testing, but really not going too in depth with that where you're adding a bunch of costs. So it's a physical performance testing criteria. Can be completed in a few hours. You can see a picture here of a bacon bomb sampler that can be used to drop down and take samples from varying levels within the tank. Generally, we like to work off of an acceptance criteria of vertical temperature gradient of not more than 1 degree Celsius along a vertical temperature curve from samples along a vertical distribution of the tank. And then total solid samples along digester cross-section not varying by more than plus or minus 10% of the arithmetic mean. And generally, we would recommend a minimum of 12 samples and 3 sample points to get a good profile of what the total solids concentrations are distributed across the tank. And we feel this is a great way to validate that you're getting that active volume that you designed for, and that the system's operating and providing homogeneous sludge for processes. And then lithium tracer testing is kind of the other physical testing that's out there. It's a physical performance testing criteria as well. But the consumable materials are becoming more and more expensive. Lithium chloride is becoming incredibly expensive as electric cars continue to grow as a market sector, and lithium costs continue to skyrocket. It's not uncommon to see lithium prices increase 200 to 400% between bid day and the time of testing. So that's something that, you know, is becoming kind of a cause for concern as far as that testing method. It can either be done as a burst or disbursement test or a washout test. And the acceptance criteria, you want to see lithium concentrations not vary by more than 10% of the mean for the dispersion test. Very similar to the total solids testing, but with a tracer element. And then for a washout test, you'd want to see the lithium concentrations throughout the washout period not vary by more than 10% from the theoretical washout curve, assuming a complete mix status of the tank. So that's kind of wrapping up the presentation. I'm going to toss it back to Steve Maycomber that's going to kind of go over a recap. Great. And then we'll get into questions.
You know, I'll just say you've seen an overview of our technology, and just want to go back to what we said in the beginning. Through all the important technical details that Eric mentioned, we want you to know Vaughan has the knowledge, the experience, you know, to help you define, to design, and to optimize, you know, an effective mixing process. We always want to maintain our focus on that. That's the overarching objective. You know, we don't want to over or under mix. All the technical product details, and there were many of them that Eric went over, they're all there for a reason. The details and the bearings, et cetera, they all come from iterative improvements that have happened at Vaughan over the years. You know, in the end, we know there's a most efficient way to mix any application, considering, you know, your capital that you have available, your operational flexibility that you need, the long-term reliability in your situation that's required. You know, are you predictive maintenance, et cetera. So we have more than 2,500 reliable installations out there, backed up by that extensive library of computational fluid dynamics that Eric mentioned. So just please don't hesitate to ask us for references. It's hard for me, probably for everyone, to not be face to face and to do this in this platform. Certainly enjoy it, but this is what we love doing, and we're here to help you define your unique mixing performance objectives. We have a lot more to talk about with you. I've just got another 300 slides to just so settle in, and we'll all just kind of continue this. So we look forward to meeting you in person when we can do that, and we'll get after it with you. So with that, I believe we're going to transition to a little Q&A for the audience. Scott, Stephanie, are you ready for that?
Yeah, thanks, Steve. Before I hand it over to Stephanie and Derek, let me just toss a few things out onto the screen, let everybody know what's going on. If you do hear a delay, maybe just check to make sure you've got a few tabs open. Maybe close those out. We'll get through this pretty easily. On the screen, I'll have Derek and Stephanie talk about the different files, but all you have to do is click those on the left-hand side and hit download, and that will bring those right to your desktop. On the right-hand side, we've got web links, so we've got links to the home page, the new video page. You can also register for future webinars, the ones that Stephanie was talking about, but also we have a new feature on here, and that's the participation certificate. So if you just click where it says participant certificate and then browse to, that will open up a new page for you, and you'll be able to provide your name and information, and then you click submit, and you'll be able to just download a participation certificate. So if you need that for any particular continuing education reasons, that's the way it goes. If you're listening to this as a recording, just email us at info@chopperpumps.com, and we will help you out from there. So, and then we always we appreciate your guys' feedback. If you've got any ideas for future webinars, then just put those right in that area. So with that, Stephanie, Derek, I'll hand it over to you.
All right. Thanks, Scott. Thank you, Eric. Thank you, Steve. That was great. Real quick, talk about these files that we have here for you guys to access. We've got some brochures about the Rotamix, fog and organics mixing that Eric talked about, some case studies. If you have any projects coming up, we've got the Rotamix inquiry form. Go ahead and fill that out and send it into info@chopperpumps or your local rep, and they can get back to you. So I am going to start. We've got a few questions here. First question from Raj. He asks, can you use Rotamix with aeration?
Yeah, and I'll take that one. So yeah, we have supplied Rotamix for aeration systems, and it's something that I think we're looking to do more of. We found a potential benefit in being able to design the aeration process for just the oxygen demand and not necessarily for a mixing specification, and using Rotamix to really reduce the size of blowers and the amount of aeration required. It's a little bit more of an intensive design, and we'd like to be more involved earlier in the project rather than on the back end. But if there's an application out there, we'd be happy to discuss it and look at what we can do to help provide a benefit to
Okay, thanks, Eric. Next question we've got here from Chris. Chris asks, would lime stabilization require a chopper pump or the Triton pump?
And, that's a great question. So lime stabilization, generally, you may be able to get away with a Triton pump. It just depends on how sure you are that what you have in that tank is just lime. So if you're potentially going to have other contamination where you might go past the ball pass for the Triton pump that you're looking at, or may cause issues for the nozzles, we may suggest a chopper pump, but definitely potentially a Triton screw pump could be the best fit for a lime stabilization application. We would just need it depends, but yes, it's potential.
All right, thanks, Eric. And we touched on CFD, but I'm going to go ahead and read Michael's question. Do you perform CFD modeling for each application before sizing the equipment and its arrangement?
Yeah, so generally we will size the equipment based on our experience, and you always need to have a first a first guess in terms of you're going to take the best information available, and you're going to find a first guess to provide an initial design, and then from there we'll start to look at CFD to better refine that design and make sure that, okay, this is what I think is going to work, but now I'm going to verify it, using that scientific method and saying, okay, I think this is the design, but now I'm going to validate it. And through that, we might iteratively end up in a much more efficient layout than what we initially had thought would work. But generally, we'll have an initial design before we do the CFD modeling, just because the chicken has to come before the egg, so to speak.
Okay, thanks, Eric. Zual asks, for which process does it work most favorable?
Yeah, so I think Rotamix is really a good fit for a lot of different processes. So I don't know if I necessarily would say that there's one that's most favorable, but I think Rotamix is a good application anytime that you're mixing something that has that's a solid laden fluid. So if you're mixing a tank that is going to have solids present, I would recommend Rotamix, whether that's a industrial, municipal, or ag application. That's really where Rotamix shines is when you're mixing a solid laden fluid like a sludge or some other waste fluid. In food. In the food industry, you might have something that's got carcasses or various other waste material, and you're trying to pre-treat that. There's a wide range of applications, but that's where it really shines, is solid laden fluids.
All right, thanks, Eric. I actually have right here Vaughan Company's chief engineer, and I'm going to defer this next question to him. I've got Arnie Swenson here. This question comes from Tyler. He asks, how can you save energy when using a Rotamix system?
Okay, so most of the time, an engineering spec will define the sludge content at say 4 to 6%, and we never want to short you on mixing capability, so we will be sizing everything for that 6%. But if you really only have 4% most of the time, we might run at 90% speed or 80% speed, whatever optimizes your gas production in the digester for the minimum amount of electricity used. Also, we have a reduced energy strategy where we run at full speed for a couple hours a day and a reduced speed the remainder of the day. Hopefully that answers your question.
Okay, Eric, Steve, do you guys have anything to add on to that or to the other questions that were asked?
I think we're in good shape.
No, I think that was good.
For follow-up emails or questions.
Yeah, if you have any questions for us, we have our contact information. Go ahead and drop us a line. And for anybody that asked questions we didn't get to, we can definitely follow up and provide answers.
Well, then let's go ahead and we'll call things wrapped up. So thank you, Steve and Eric, Stephanie, and Arnie. If you guys have any other questions that we didn't get to today, or you're listening to this on demand, just email us at info@chopperpumps.com or contact your local sales rep. Real quick, if you haven't already and you want that participation certificate, just in that web links box on the bottom right-hand side, just click Participant Certificate and then Browse to. That will open up a new window for you, and you'll just fill out the form and be able to download it right there on the spot. Okay, next webinar is scheduled for May 19th with That's Not a Digester, how to mix blend tanks, storage tanks, EQ basins, and more. You can learn more and register at chopperpumps.com. And with that, Stephanie, I think we're good for the day. Thanks, everybody.
All right, thanks, everybody.